Welcome back. In this video, we are going to solve problem 12-48 that is taken from chapter number 12, Deflection of Beam and Shaft, and book name is Mechanics of Material by RC Hibbeler. So statement is the wooden beam is subjected to the load shown. Determine the equation of elastic curve. Specify the deflection at end C. E of wood is 1.6 into 10 raised to power 6 ksi. So you can see this is the wooden beam that is overhanging beam, and from point A to B there is a triangular load or uniformly increasing load that is 0.6 kips per feet, and at point end C we have 1.5 kips load. The cross section of this beam is shown. Width is 6 inch and height is 12 inch. So let's start with the solution. So we have to find equation of elastic curve, and we have to find deflection at point C. Deflection at point C, which is equal to VC. So solution is, the first step is that if you remove this reaction, if you remove the support at point A, so you'll be having reaction force. Let this is in downward direction, and this is RA, and if you remove this roller support at point A, so you'll be having reaction force in upward direction, that is RB. So you can take it as per your own convenience, and from the answer you will judge it whether you have taken the right direction or not. So let's start finding RB. So RB can be obtained by applying the equation of equilibrium, that sum of all moments about point A is equal to 0, taking the counterclockwise moment as positive. So you can see there is a triangular load of 0.8 kips per feet. If we convert this triangular load into a point load, so this is a triangular area, so it can be obtained by formula 1/2 into this 0.8 into the length over which it acts, and that is 0.9, and that is equal to 3.6, and that will be act at a distance of L/3 from this denser side. So L/3 length is 9, so L/3 9/3 is 3 meter, and this remaining distance will be equal to 6 meter. So a moment about point A is produced due to this load, and perpendicular distance is 6, and this is producing clockwise, so it will be negative. So I will write 3.6 into perpendicular distance is 6. The second moment is produced due to this RB into perpendicular distance is 9 feet, and this is producing counterclockwise, so it will be positive. So I will write plus RB into 9. The third moment is produced due to this load 1.5 kips, and perpendicular distance is 18, and this is producing clockwise, so it will be negative. So I will write minus 1.5 into 18 is equal to 0. So I will get minus 21.6 plus 9 RB minus 27 is equal to 0. Okay. So 9 RB will be equal to 21.6 plus 27, and you will get RB will be equal to 21.6 plus 27 is actually 48.6, and if you divide 9 on both sides, so you will get RB will be equal to 5.4 kip. Now you have this RB clear. We can find RA by using another equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward force taken as positive. So RA, which is downward, so minus RA, this force 3.6 that is downward, so minus 3.6 plus 5.4 is RB minus 1.5 is equal to 0. So again, when you calculate it, you will get RA is equal to 0.3 kips. Since this is positive value, it means that you have taken the correct direction of reaction force RA and RB. Now you can see We are interested to find out equation of elastic curve that can be obtained by using this formula. EI into d square V over dx square is equal to moment, and this moment can be obtained by using Macaulay's method. Okay, so we'll apply Macaulay's method to find out this moment m. Now you can see here from this figure that there is a point load, there is triangular load, point load, and again point load. So we will start from left hand side and we will move toward right hand side, and at right hand side you will neglect this force. Also the loading is shown in the table. For point load we will use the moment equation, this one, and for this load, triangular load, we will use this equation. Okay, if you look at 4 number, this triangular load start from anywhere but it is till the end, and this here this load start from A till B. So what we will do is we will add further load over here and we will convert it into triangular load like this, and at the end we will subtract the same load but in the opposite direction, so that we can easily apply this table. So I will draw the free body diagram over here. So this is the beam, this is your point A, where is a load of RA is 0.3 kips, clear, and at point B we have a load of RB, that is 5.4 kips. This distance is 9, clear, 9 feet, and the remaining distance is also 9. Okay, so from what we will do is that we will add this load from first point till the last end. This was the load till this, and that is 0.8 kips per feet, that is triangular load downward, and you can see this is over length of 9 feet. So this is again 9 feet, so this load will be double, so it will be 1.6 kips per feet, and that will be downward. What we have done is that we will add this load 0.8 and this load in the opposite direction, so it should cancel the effect. So we will choose another color. This is 0.8 kips per feet, so from here and then till the last here the load is 1.6 kips per feet, and this should be in upward direction. Okay, now you can see this 0.8 is, if we treat it like uniformly distributed load, so till this it will be 0.8 kips per feet, and from here it will be 0.8 to 1.6, and at the end we have a point load of 1.5 kips as well. So this is 1.5 kips load. Now apply this moment equation. So this moment M will be equal to, the first load is this 0.3 kips and that is acting downward. So this moment equation will be -1. So I will write this moment is equal to -0.3 into x minus a is equal to 0, because this load start at the beginning. So this will be -0.3 into x minus 0. The second load is this uniformly increasing load, and you can see for uniformly increasing load the moment equation is this one, where m is the slope. So we will find this m. So this m will be equal to perpendicular, which is 1.6, divided by base, which is total 18. So this is m. So this load is upward and this is downward. So I will write minus m by 6. So m by 6 is 1.1 by 6 multiplied by m, which is 1.6 divided by 18 into the x minus a. So x minus a is equal to 0 for this load. So x minus 0 power 3. The third load is this load, which is 5.4, and this is upward, so we will use this equation. So plus 5.4 into x minus a is 9 for this. So x minus 9 power 1. The fourth load is this uniformly distributed load of 0.8 kips per feet. So distributed load is like this. So I will write this load is upward. So it will be plus W naught is 0.8 divided by 2 into x minus 9 power 2. Okay, and the last load is this uniformly increasing load that start from 0.8 till 1.16. So slope m for this will be equal to perpendicular, which is 1 point. This is again this height, this remaining height will be 0.8. So 0.8 divided by this base, which is 9 feet. So this will be the m. So m is equal to 0.8 divided by 9. And you can see this load is upward, so this will be positive. So plus m, which is m by 6, so 1 by 6 into m is 0.8 divided by 9 into x minus a. A for this is again 9. This 9 power 3. So this is your moment equation, and if you simplify this moment equation, you will get minus 0.3 times x minus 0.0148 x cube plus 5.4 into x minus 9 and plus 0.4 times x minus 9 square plus 0.0148 into x minus 9. So this was the most difficult step in this problem. This is your equation number A. Now it's very easy. Put the value of m in equation A. Put value of m in equation A. So you will get EI into d square V over dx square will be equal to minus 0.3 times x minus 0.0148 x cube plus 5.4 into x minus 9 plus 0.4 into x minus 9 power 2 plus 0.0148 into x minus 9 power 3. So what we will do is that we will integrate this equation. Integrate it, you will get EI into dV over dx will be equal to minus 0.3 x square over 2, which will give you minus 0.15 x square. The second term minus 0.014 x power 4 divided by 4, and this will give you 0.00370 x power 4 plus 5.4 into x minus 9 power 2 divided by 2, which is equal to 2.7 into x minus 9 power 2 plus 0.4 into x minus 9 whole cube divided by 3, which will be equal to 0.1333 into x minus 9 power 3 plus 0.0148 x minus 9 power 4 divided by 4 will be equal to 0.003704 into x minus 9 power 4 plus C1, which is the constant of integration. This is your equation number 1. Now integrate this equation 1. So you will get EI into V is equal to minus 0.15 x cube divided by 2, which is equal to minus 0.0 minus 0.15 x cube divided by 3, which is equal to minus 0.05 x cube minus 0.003704 x power 5 divided by 5 will give you 0.000740 7x power 5 plus 2.7 into x minus 9 power 3 divided by 3 will be equal to 0.9 into x minus 9 power 3 plus 0.133 into x minus 9 power 4 divided by 4 will give you plus 0.3333 into x minus 9 power 4 plus this will be equal to 0.0007407 into x minus 9 power 5 plus c1x plus c2. Let this is your equation number 2. Now c1 and c2 are unknown constant, and by using boundary condition we will find these two, C1 and C2. So what are the boundary conditions? So first boundary condition is that at x is equal to 0 we have deflection is equal to 0. So let me show you over here. You can see at x is equal to 0 we have deflection is equal to 0 because there is a pin support at point A. So what we will that put in equation number 2. So when you put it in equation 2, so this will be 0 because v is equal to 0, this will be 0, x is 0, this will be 0, minus 9 inside the Macaulay bracket will be considered as 0, this will be 0, this will be 0, c1 into x will be 0, so we will left with c2 is equal to 0. So c2 will equal to 0. So you have to perform this step so that one can understand. Now the second boundary condition is that at x is equal to 9 feet, we have v is equal to 0. So let me show you again. Here you can see at x is equal to 9 feet, we have deflection is equal to 0 because there is a roller support. So put in equation number 2. So ei into 0 is equal to minus 0.05 into 9 cube minus 0.0007407 into 9 power 5 plus 0.9 into 9 minus 9 power 3 plus 0.03333 into 9 minus 9 power 4 plus 0.0007407 into 9 minus 9 power 5 plus c1 into 9 which is 9c1 and c2 is equal to 0. So this will be equal to 0, this will be minus 36.45 minus the second term will be 43.74, this term will be 0, this will be 0, this will be 0, so plus 9 times c1. So from here you will get c1 will be equal to 8.91. Now you have c1 is equal to 8.91 and what we have been asked to find, so equation of elastic curve and deflection at point C. So what we will do is that put the value of c1 and c2 in equation number 2 in equation 2 and divide ei on both sides to get the equation of elastic curve. So you will get v is equal to 1 over ei into minus 0.05 x cube minus 0.0007407 x power 5 plus 0.9 into x minus 9 power 3 plus 0.0333 into x minus 9 power 4 plus 0.0007407 into x minus 9 power 5 plus c1. c1 is 8.91 x1 and c2 is equal to 0 is required equation of elastic curve. So this is equation of deflection. So if you want to find deflection and at any x distance, so put the value, you will get the deflection. In our next part we have to find deflection at point C. So at x is equal to 18 feet. So deflection is equal to VC. So put what we will do is that put x is equal to 18 feet. So what we'll do is that in above equation of elastic curve, you will get V is equal to 1 over E into I, and that will be minus 0.05 into 18 cube minus 0.000747 into 18 power 5 minus plus 0.9 into 18 minus 9 power 3 plus 0.0333 into 18 minus 9 power 4 plus 0.000747 into 18 minus 9 power 5 plus 8.9 into 18. So when you solve this, you will get this V, that is displacement at C, will be equal to 1 over EI times minus 612.36, and the unit will be kips into cubic feet. Now we have been given that E of wood is given as 1.6 into 10 raised to power 3 ksi, and the cross section of this beam is given as, so we will find I. So I is equal to 1 over 12 bh cube. So 1 over 12 into b is 6 inch and height is 12 inch cube. So we will put the value downward. So from here 1 over E of wood is given as 1.6 into 10 raised to power 3 ksi. So 1.6 into 10 raised to power 3 ksi into I is 1 over 12 into b was 6 and height was 12 cube. So it will be inch power 4. Multiply by minus 612.36, and we will convert it into feet, inch. So there is feet, so 1 feet is equal to 12 inch, so 12 cube. And when you solve this, you will get VC will be equal to minus 0.765 inch. Or you can see that VC deflection at point C is 0.765 inch, and that is downward. So this is the answer of our second part. And that was all about this problem 12-48. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest video. Also comments on my videos whether you like it or not, and if you want to suggest any improvement, you can tell me in the comment section. Thank you for watching. Welcome back. Problem 12-49, and this problem is taken from chapter number 12, that is Deflection of Beam and Shaft, and book name is Mechanics of Material by RC Hibbeler. So statement is determine the displacement C and slope at A of the beam EI is constant. So you can see this is overhanging beam and loading shown from C to A there is a uniformly distributed load, and then from A to B there is a uniformly decreasing load or triangular load. X start from here, total length of the beam is 15 feet, and at point A there is a roller support, and at point B there is pin support. So due to this loading, the beam will deflect like this. Clear? So we have to find the displacement of at point C, which is VC, and the slope, which is the tangent slope theta A, which is equal to tangent of this line. So let's start with the solution. step is that if you remove the roller support at point A, so you will be having reaction force which is represented as RA. And if you remove this pin support at point B, so you will be having a horizontal reaction force which is equal to RBX, because it's horizontal component, and there will be a vertical component as well which will be RBY. So we have taken RBY downward. You can take it upward, and when you calculate it, if the value comes out to be negative, it means that your selected direction is wrong and it should be in opposite direction. So you'll find this RA, RBY and Rx by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. So you can see only there is a one horizontal force which is RBX, and there is no other force. So RBX, it means that RBX is equal to 0. So this pin support does not offer horizontal reaction force. Now we will find this RA and BY by using another equation of equilibrium, that is sum of all moments about point B is equal to 0, and taking the counterclockwise movement as positive. Before doing this, you can see there is a distributed load, uniformly distributed load from A to C. So when this is converted into a point load, so you have to multiply this distributed load of 8 kips per feet with the length which is 6, and this will be equal to 48, and this will act at a distance of half of the 6 feet. So it means that this distance is 3 feet. And there is a uniformly decreasing load from this point till this point. And when you convert this load into a point load, so it will be, as it is triangular, so area of this triangular is 1/2 into 8 into length, which is 9. So I will convert this uniformly decreasing load or triangular load into point load, and it will be equal to 1/2 this magnitude of 8, because this is the maximum, into length which is 9, and this will be equal to 36. Now it is acting at a distance of L/3 from this denser side. This is the denser side. So this distance will be L/3, and the length of this over portion which it is act is 9. So 9/3 is equal to 3. So this distance will be equal to 3 feet. And the remaining this distance will be equal to 6 feet. Okay. Now sum of all moment about point B is equal to 0. So these two forces do not produce any moment because it is passing through this point. So first moment will be produced due to this load which is equal to this 36 into perpendicular distance is 6, and this is producing counterclockwise movement, so it will be positive. The second movement will be due to this RA into perpendicular distance 9, and this is producing clockwise, so it will be negative. The third movement will be produced due to this 48 load and perpendicular distance is 12, and this is producing counterclockwise, so it will be positive. And the sum of all moment about point B will be equal to 0. So I will write first 36 into 6 minus 9, which RA into 9 plus 48 into 12 is equal to 0. So from here you will get 36 into 6 is 216 minus 9RA plus 576 is equal to 0. So it means that 9RA is equal to 792, and when you divide 9 on both sides, so you will get RA will be equal to 88 kips. RA value is positive, so it means that you have taken the direction of RA is correct. Now we will find RB by using another equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So you can see RB is downward, this 36 is downward, plus RA minus 48 will be equal to 0. So I will write minus 48 minus 48 minus 36 plus RA, which is 88 kips, minus RBY is equal to 0. So when you calculate it, you will get RBY will be equal to 4 kips. Since this value comes out to be positive, it means that you have chosen the RBY in downward direction is correct one. Now you have all these forces, so we will find the equation of elastic curve by using the equation EI into d square V over dx square is equal to moment. So we'll find the moment by using discontinuity equation or using Macaulay's method. Now you can see that this beam having loading or uniformly distributed load, then triangular load, then you have a point load. So it's a mixture of all the loads, and you can see the table below having point load, distributed load, and triangular load and their moment function. So for this beam, we will calculate this M by using this moment function. So if I draw the free body diagram of this beam, so it is like this. We have, let this point is RA, so we have RA is 88 kips, clear, and there is a uniformly distributed load of 8 kips per feet, and then triangular load which is downward. Now from the table you can, and there is RB Y which is downward, and this RBY is 4 kips, and there is no RAX which is 0, RBX. Now you can see from this table that for point load we have a moment function is this one. For distributed load, so distributed load start from this till the end. If A is equal to 0, it means that it start from till end. And here you can see the load is, distributed load is from till up till of length of 6 feet. So what we will do is that we will add a triangular load like this to make it completely distributed load. And in downward direction, we will subtract the same in upward direction. So let's do this. We will choose another color. We will add the same load in downward direction. Okay, and in downward direction, we will add the same thing, but will be in the upward direction. This point start from there. Okay. And this magnitude here, this is total 8. So this will be also 8 kips per feet. Now let's start with the moment function. So I will write moment will be equal to, first we will consider this distributed load of 8 kips over the whole length, and for this we have function M is equal to W naught over 2 into X minus A. So W naught here is 8, so 8 by 2, and this load is downward and here load is upward, so this moment is positive. But here the load is downward, so it will be minus 8 by 2 into X minus A is equal to 0, because moment start from here. A is equal to 0 for this load, and X start from here. So X minus 0 power 2. Okay. The second moment that is produced due to this load, this point load, which is 88, and this is upward. So for point load, the function is this one. So I will write plus P into X minus A is here 6 feet, because X start from here and this load is at a distance of 6 feet. So X minus 6 power 1. The third load is triangular load, and you can see this load is like this. So for triangular load, the moment is m by 6 into x minus 6, x minus a power 3. What is m? So m is the slope of this curve. Slope is equal to tangent theta, which is equal to perpendicular, and this perpendicular is 8 divided by this base, which is equal to 9 feet. So 8 by 9. Clear? And this load is upward, and here the load is also upward, so it will be plus, you can see, m by 6. So m is 8 by 9 into 1 by 6, which is m by 6 into x minus a. A is 6, so x minus 6 power 3. And we will neglect the last load, RBY. Okay, so this is the function. Let this is equation number A. So put value of m in equation A. So you will get EI into d square V over dx square will be equal to minus 4x square. Clear? And this term 8 by 9 into 1 over 6 will be equal to plus 4 over 27 into x minus 6 power 3, and this term will be equal to plus p. So p here is 88. Okay, this is 88. So 88 into x minus 6. What we will do is that integrate it. So when you integrate it, you will get EI into dV over dx will be equal to minus 4x cube over 3 plus 4 over 27 into x minus 6 power 4 divided by 4 plus 88 into x minus 6 power 2 divided by 2. And if you further simplify it, it will be equal to minus 4 over 3 x cube plus x minus 6 power 4 divided by 27 plus 44 into x minus 6 whole square, and there will be a constant of integration as well over here, plus C1. So C1 will be over here. Let this is your equation number 1. Now what we will do is that again integrate equation 1. You will get EI into V is equal to minus 4x power 4 divided by 3 into 4 plus 4, this is x minus, this is the equation, this one, x minus 6 into 5 divided by 27 into 5, clear, plus 44 into x minus 6 power cube divided by 3 plus C1x plus C2. And again if you simplify it, it will be equal to minus x4 over 3 plus x minus 6 power 5 divided by 135 plus 44 by 3 into x minus 6 power 3 plus C1x plus C2. This will be equal to EI into V. Let this is your equation number 2. Now C1 and C2 are unknown constant of integration, and they can be found by using boundary condition. So I will write boundary conditions. So first boundary condition is that at x is equal to 6 feet, we have deflection is equal to 0. So let me show you here x is equal to 6 feet we have deflection is equal to 0 because there is a roller support. So put it in equation number 2. When you put it in equation number 2, so this is equation number 2. So EI into V, which is 0, is equal to 0, and minus 6 power minus 1 over 3 into 6 power 4 plus 6 minus 6 power 5 divided by 135 plus 44 over 3 into 6 minus 6 power cube plus C1 into 6 plus C2. So this term will give you minus 432. This will be 0 because 6 minus 6 is 0. This term will be 0. So we have 6C1 plus C2 is equal to 0. So from here you will get 6C1 plus C2 is equal to 432. Let this is your equation number 3. Now the second boundary condition is that at x is equal to 15 feet, we have deflection is equal to 0. So let me show you here. Here x is equal to total length is 15 feet and we have deflection is equal to 0 because there is a pin support at point B. So put in equation number 2. So what you will get, EI into V is equal to 0 is minus 1 over 3 into 15 cube, 15 power 4 plus 15 minus 6 whole power 5 divided by 135 plus 44 by 3 into 15 minus 6 power 3 plus C1 into x, which is 15. So 15 C1 plus C2 is equal to 0. So again you will get this is equal to 0. All these terms will give you, when you calculate it, will give you minus 5745.6 plus 15 C1 plus C2 is equal to 0. So from here you will get 15 C1 plus C2 is equal to 5745.6. Let this is equation number 4. So equation 3 and 4 are simultaneous equation, so you can easily solve this. So solve equation 3 and 4 simultaneously. You will get C1 will be equal to 509.4. I hope you can do this step by your own self. So these are the value of C1 and C2. Now in first part we have been asked to find the displacement of point C, and in second part slope of point at A. So for displacement, what we'll do is that put the value of C1 and C2 in equation number 2. This is the equation number 2, and divide EI on both sides. So you will get deflection is equal to 1 over E into I into minus x power 4 over 3 plus x minus 6 power 5 divided by 135 plus 44 over 3 into x minus 6 power 3 plus C1, which is 509.4 into x plus C2, and C2 is minus 3110.4, and the unit will be, after putting the value of unit of E and I, so you will get the unit will be in feet, or you can just say it is keeps into cubic feet, and when you put the value unit of E and I, so definitely it will convert into feet. Now we have to find V at C, so it means that you have put X is equal to 0, so you will get VC. So put X is equal to 0 in this equation, so this deflection will be equal to VC, or V at X is equal to 0, and this will be equal to 1 over E into I. This term will be 0 because this term will be equal to minus 6 if you put X. So anything that is negative inside the Macaulay bracket will be 0. Similarly, this term will be 0, this term will be 0. So we will left only with this term. So it will be equal to minus 3110.4. And this will be equal to minus 3110.4 divided by E into I. And it will be equal to, unit will be kips into cubic feet. So if you have the unit of E and I, so you will put at the end, you will get this VC will be equal to minus 3110 divided by E into I kips into feet. The negative sign shows that displacement or deflection will be downward. So this is the answer of our first part. Now we will move toward next part, that is to determine the slope at A. So what we will do is that we will copy the equation number 1. So where is equation number 1? So let me copy it. This is equation number 1. So remember the value of C1 and C2. This is equation number 1. So put C1 in equation number 1 and divide EI on both sides. You will get dV over dx is equal to minus 4 over 3 into x cube plus x minus 6 power 4 divided by 27 plus 44 into x minus 6 power 2 plus C1, and it is wholly divided with 1 multiplied with 1 over EI. Okay. C1 value was plus 509, so I will replace 590.4. Now we have to find the slope at point A. So here x is equal to 6 feet, and I have already shown you, due to this the deflection will be like this. So slope at this theta A will be equal to at 6 feet. So when you put x is equal to, at x is equal to 6 feet, we have dv over dx at x is equal to 6 is equal to slope at A. So dv over dx is theta, and that will be equal to minus 1 over EI into minus 4 over 3 and 6 cube plus 6 minus 6 power 4 divided by 27 plus 44 into 6 minus 6 square plus 590.4. So this 1 over EI, clear, and this term will be 0, this term will be 0, and the sum of this term and this term will give you 302, and the unit will be kips into cubic feet square, theta A. Okay. And theta A slope at point A is equal to 302 divided by E into I, kips into square feet. So this is the slope at point A, and that is the answer of our second part. And that was all about this problem 12-49. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 12-50, and this problem is taken from chapter number 12, Deflection of Beam and Shaft. And book name is Mechanics of Material by RC Hibbeler. So statement is the beam is subjected to load shown, determine the equation of slope and equation of elastic curve EI is constant. So you can see this is overhanging beam, and at point A we have a pin support and at point B we have a roller support. From A to B we have a uniformly distributed load of 3 kilonewton per meter, and at end C we have a moment that is clockwise and 50 kilonewton into meter. So we have to find the equation of slope and elastic curve, and we will solve this by using Macaulay's method. So let's start with the solution. So first step is, if we draw the free body diagram, so we have to remove this support at point A. So if you remove it, you will be having a reaction force. Let this is RA, and if you remove this support at point B, roller support at point B, so you will be having a reaction force which will be equal to RB. So you can take it as per your convenience, the direction of this force, and from the value you will obtain, you will guess whether you have taken the corrected direction or not. So let's find the moment, this RB, by using in equation of equilibrium, that sum of all moments about point A is equal to 0, taking the counterclockwise movement as positive. So about point A, first movement will be this RB into perpendicular distance is 5, and this is producing counterclockwise, so it will be positive. So I will write RB into 5. The second movement is this external movement that is clockwise, and 15 kilonewton into meter, and the third movement is this uniformly distributed load due to this load. And when we convert this load into a point load, so it will be 3 into the length over which it acts, and that will be acting at half of the length, which is 5 divided by 2, and this is 2.5, and this is producing clockwise movement, so it will be negative. So I will convert this uniformly distributed load into point load. So 3 into 5 is equal to 15 kilonewton, and that is acting at half, which is 2.5 meter. So I will write minus 15 into 2.5 is equal to 0. So when you solve this, you will get this RB comes out to be 10.5 kilonewton. Now you have this RB, you can find this RA by using equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So RA, which is acting upwards, so it will be positive, minus this 15 kilonewton, that will be downward, plus RB, which is 10.5, is equal to 0. So from here you will get RA will be equal to 4.5 kilonewton. Now you have both RA and RB, so we will find the equation of slope and deflection by using this equation, and the equation is EI into d square V over dx square is equal to moment. So by moment can be obtained by using Macaulay's method. And for this method, we will use the table given in the chapter number 12 of the book, Mechanics of Material by RC Hibbeler. So this is the table, and from this table you can see that you have the case of point loads, you have distributed load and point loads, etc. So we'll start from left hand side and we will move toward right hand side, and at right hand side you will ignore the load. So if I look into the table, so there is a point load, the moment function will be this one, and you can see there is a distributed load in 3, serial number 3. So this distributed load start from any point, but it ends up till the last. In our case, our distributed load start from point A till B. So we have to make it till the end. So what we will do is that we are going to add the uniformly distributed load from B to C as well, clear, and then we will subtract it downward by giving the upward direction. So let me draw the free body diagram. So this is the beam. Okay, you have a load RA which is upward, and RA is 4.5 kilonewton, and at point B you have a load of 10.5 kilonewton, clear. And from A to B, this is point A, this is your point B. So from A to B there was a uniformly distributed load like this, and it was downward. The magnitude is 3 kilonewton per meter. So what we will do is that this is point C, and at point C we have 15 kilonewton into meter moment. So what we will do is that we will add the same 3 kilonewton per meter force over here, and from B to C in the bottom we will subtract it, so that it should cancel the effect, and this should be in opposite direction. So this is 3 kilonewton per meter. Now we will find this moment equation. So this moment equation for first this point load. So this point load is upward, and here the load is also upward. So we'll use this case, and the moment function will be equal to 4.5 into x minus a is equal to 0 in this condition. So this will be equal to x minus 0 power 1. The second load is this uniformly distributed load, and this start from A till C, and this is kilonewton, 3 kilonewton per meter. So its function will be this one, and the load, you can see this is downward, and here the distributed load is upward, so moment is positive. So here we will take the negative because it is downward. So W naught, which is 3 kilonewton per meter, so 3 over 2 into x minus a is equal to 0, because this load start from end A. So x minus 0 power 2. The third load is this point load, and this is upward, clear. So 10.5, and this distance is 5 meter, you can see over here. So I will write plus 10.5 into x minus 5 power 1. And the last load is from B to C is uniformly distributed load. Now this load is upward, and so it will be positive. So I will use this equation. So plus W naught is 3 over 2 into x minus a. So this distance is 5 meter. So x minus 5 power x minus 5 power 2. Okay, so if we simplify this equation, the moment equation will be equal to 4.5x minus 1.5 times x minus 1.5 times x square plus 10.5 into x minus 5 plus 1.5 times x minus 5 power 2. So this is your moment equation, and let this is your equation number A. So what we will do is that put the value of m, put value of m in equation A. So what we will get is EI into d square V over dx square will be equal to 4.5x minus 1.5x square plus 10.5 into x minus 5 plus 1.5 into x minus 5 square. Integrate this equation, we will get EI into dV over dx will be equal to 4.5 x square divided by 2 minus 1.5 x cube over 3 plus 10.5 into x minus 5 power 2 divided by 2 plus 1.5 into x minus 5 whole cube divided by 3 plus constant of integration, which is equal to C1. So if you further simplify it, so you will get EI into dV over dx will be equal to 2.25 x square minus 0.5 x cube plus 5.25 into x minus 5 power square plus 0.5 into x minus 5 power 3 plus C1. Now this is your equation number 1. So integrate this equation 1, you will get EI into V, which is deflection, is equal to 2.25 x cube divided by 3 minus 0.5 x power 4 divided by 4 plus 5.25 into x minus 5 power 3 divided by 3 plus 0.5 into x minus 5 power 4 divided by 4 plus C1x, and there will be another constant of integration which is equal to C2. So if you further simplify it, so you will get EI into V is equal to 0.75 x cube minus 0.125 x power 4 plus 1.75 into x minus 5 power 3 plus 0.125 into x minus 5 power 4 plus C1x plus C2. And this is your equation number 2. Now C1 and C2 are unknown constant of integration, so boundary conditions will be used to find C1 and C2. So what are the boundary conditions? So first boundary condition is that at x is equal to 0, we have deflection is equal to 0. So here you can see x is equal to 0, we have deflection is equal to 0 because at point A we have a pin support. So put it in equation number 1. Put in equation 1. So when you put it in equation number 2, because equation number 2 is for deflection. So when you put it, this term will be 0, this will be 0, this will be 0, this will be minus 5. So anything inside the Macaulay bracket that is negative will be 0. This term will be 0. C1 into x will be 0. So we left with C2. So C2 will be equal to 0. So from here you will get C2 will be equal to 0. You can just put the value and you can do these steps. Now we will apply second boundary condition. So at x is equal to 5 meter, you can see x is equal to 5 meter, we have deflection is equal to 0. So here x is equal to 5 meter, we have deflection is equal to 0 because there is a roller support over here. So put it in equation number 2. Put in equation 2. So when you put it, you will get E into I multiplied by 0 will be equal to 0.75 into 5 cube minus 0.125 into 5 power 4 plus 1.75 into 5 minus 5 power 3 plus 0.125 into x minus 5 minus 5, x is 5 power 4 plus C1 into 5 and C2 is equal to 0. So you will get 0 will be equal to 93.75 minus 78.125. This term will be 0. This term will be 0. So we will left with 5 times C1. And when you calculate this, you will get C1 will be equal to minus 3.125. Now you have C1 and C2. So what you will do is that put C1 in equation number 1. You will get EI into dV over dx will be equal to 2.25 x square minus 0.5 x cube plus 5.25 into x minus 5 square plus 0.5 into x minus 5 cube plus C1. C1 is minus 3.125. And if you divide EI on both sides, so you will get dV over dx will be equal to 1 over EI times 2.25 x square plus minus 0.5 x cube plus 5.25 into x minus 5 cube square plus 0.5 into x minus 5 whole cube minus 3.125. And this is dV over dx is equal to slope, which is the required equation of slope. Now what we will do is that put C1 and C2 in equation number 2. Put C1 and C2 in equation 2 and divide EI on both sides. So you will get V is equal to 1 over EI into 0.75 x cube minus 0.125 x power 4 plus 1.75 into x minus 5 whole cube plus 0.125 into x minus 5 whole power 4 plus C1x. So C1 is minus 3.125x and C2 is equal to 0. And this is the required equation of deflection or required equation of elastic curve. So if you want to find at any distance of x the slope and deflection, so just put the value of x over here, you will get the slope at that distance of x. And if you want deflection, so put the x in this deflection formula, so you will get the deflection at that point. And that was all about this problem 12-50. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest video which I post. Also comment on my videos whether you like it or not and suggest me the improvement. If you have any question, you can ask me in comment section. Thank you for watching.